Hey everyone, we're going to be going over part 2 of module 14 for physical science. Um, and we're going to start by doing an experiment, but sort of a modified version of experiment 14.3. You don't have to do a lab report for this or anything. But we're just going to be talking about how wavelength affects pitch. So, remember that wavelength for a transverse wave is going to be the distance from crest to crest or trough to trough. Both of these are wavelength, and here's the lambda, the symbol for wavelength. We're dealing with sound though, and sound, is it a transverse wave like that? No. Sound is going to be a longitudinal wave. Remember, a transverse wave is like an elephant walking and flailing its trunk, whereas this is more like a chicken. Longitudinal wave is more like a chicken, like bobbing its head in the same direction it's walking. If that doesn't make any sense to you, I'm not going to bother explaining it. So longitudinal waves, we have compressions and rarefactions. And a wavelength in a sound wave is going to be the distance from compression to compression, or rarefaction to rarefaction, and I'm just drawing it from any place in the compression or the rarefaction as long as it's the same place in the other one. So those are our wavelengths, and it turns out that wavelength is going to have a profound effect on pitch. You know what, actually I shouldn't erase this just yet. And we'll talk about that for a moment. So imagine you have this length of wave traveling at a certain speed such that every single second this section of wave will cross this point. So what would be the frequency of this section of wave? This wave's frequency is going to be how many times or how many wavelengths cross a certain point per second. So how many wavelengths do we have here? Basically 1, 2. So this is 2 wavelengths, and if every second 2 wavelengths cross here, then we'd be traveling at 2 wavelengths per second, aka 2 hertz. But if on the other hand you have a wave traveling at the same speed, but it has smaller wavelengths, then this would be 1, 2, 3 wavelengths crossing per second. Or 3 hertz. So the frequency of this one is 2 hertz, the frequency of this one is 3 hertz. And let's ask ourselves again, what does frequency actually do to a sound wave? The higher the frequency, in other words, the higher the number of hertz, the higher pitch the sound will be. So a 3 hertz wave is going to be a higher note than a 2 hertz wave. And so frequency is the energy of the wave, but it's also going to determine the pitch. Now, something interesting happens with musical instruments. If you have just a note on the guitar, like right here, I'm just going to take this string. This is the low E string, so it's the lowest note. And I pluck it, and this is basically doing experiment 14.3, but in our own way. If I pluck this note, then if I were to do slow motion, which I can't, just take a close look at this string, you might see that string is vibrating. So the sound wave is propagating from the guitar, but and the sound wave and the oscillation are going to be like going in the same direction. The propagation and oscillation are parallel for a longitudinal wave, but you see the vibration. Now, this particular string is able to have long wavelengths because the string is stretched this long, so the wavelengths can be longer if they're generated by a long string. What if I were to take this string and clamp it in half? You see this point on the guitar? This is fret 12, and it's got a double dot, because this is where, if I put my finger there, it's going to clamp the string exactly in half. So here's a low E, then here's a high E. So this is long wavelengths, short wavelengths, long wavelengths, short wavelengths. And what I'm actually doing is I am clamping in half the distance that the wave can travel along the string as it's oscillating the string, and thus I am actually taking it an entire octave up. This is not in the book, but there was a Greek mathematician by the name of shoot, I'm blanking. Was this Pythagoras who was the father of music? I know he did the Pythagorean theorem, but let me pause and confirm. Yes, it was Pythagoras. So Pythagoras realized there's a certain ratio between the space in musical notes, and so if you do take basically the space that a sound wave has to oscillate, and you cut it in half, then you're going to be going up one octave. Now I can cut this in half again, although this is a little bit harder this time. And this will be a fourth of the length of the original string, so somewhere around here. Right about there. So low E, higher E, higher E. And now if I take this and I clamp it in half again, right around there, that's an even higher E. So low, higher, higher, and then there we go. So approximately that was 4 octaves of E, and all I did was I used Pythagoras ratio and just clamped the string in half 4 different times, or 3 different times, because the first one wasn't doing that. Now, this is probably going to fail miserably, because I'm really bad at this. Actually, no, I'm not going to do that yet. First, I'm going to do this with a flute. This is one of my Native American flutes. This is not the one that I can play well. This is a 5-hold one, and I'm good at like a 6-hold one. But so with each of these 5 holes, when you put your fingers down on the holes, what you're doing is you're lengthening the chamber through which the sound waves can oscillate. And so, in other words, they can have longer wavelengths the more fingers you put down. So a lower note the more fingers you put down. So here is just no fingers. Very shrill, very high-pitched. Sounds like a tea kettle. Then I put down 1 finger, a little lower, another finger, lower, next one. And I could probably play something that's like, this is a pentatonic scale, I believe. Yeah. Yeah, so that's much of the Hobbit song as I can probably do on this. Alright, so now I'm interested. I want to see if I can play something. Alright, so if I had like my normal flute, I could do this really well, but here's an attempt at the Chorus of 10,000 Reasons, because it's got the right range roughly. Let's see. You can also have, like, for example, if it's like steel drums or something like that, just kind of, you hit a big drum, it's going to be a low note because there's a lot of room for the wavelength to kind of expand. You hit a little drum, it's going to be a higher note. And even like if you have a reed instrument, then what you have is like little tiny reeds that you blow air across them and they vibrate. And if I had my, actually I do have my harmonicas, goodness. Okay, so I'm just throwing things in right now, but I'll get a harmonica. All right, so here's a harmonica. I'll try like Amazing Grace or something. No, I can't do that because it doesn't have note 6 down there. Let me see. I'm gonna think. Okay, I can do it on a higher octave, so. So the way the harmonica works, if I were to open it up, is you have all these tiny reeds that are arranged kind of like a xylophone or glockenspiel or something. And I kind of have these in reverse order for how a harmonica really has them. But as you blow across them, they vibrate, and that's how a reed instrument works. So you vibrate a small reed, and there, it's vibrating. So the bigger reeds are going to vibrate and make lower notes because they have higher wavelengths, more space to for the wavelength to stretch out. So that's a big reed. And then the little reeds, you blow into them and it vibrates them. And there's less space for the wavelength to expand. And so smaller wavelength equals higher frequency, which equals higher pitch. One last attempt at demonstrating these concepts, and this is where I'm going to probably fail miserably. This is like a reeds ginger ale type thing, I guess. But yeah, I can never do this. Anyway, I'm terrible at blowing in bottles. But you can do this at home. Take a bottle. This is optional, but it's pretty fun. Take a bottle and just blow into it. It'll make a certain pitch, even though I'm not doing it right. I can play tons of instruments. I can't whistle and I can't do this. Then this is kind of a high pitch. Then pour some water out, and you're expanding the amount of air, the space for the air to oscillate with the sound wave. Now listen to this. So even though I'm not making the sound I'm trying to make, you can still hear it's a lower pitch. And now I'm going to empty it, and you'll hear a much lower pitch. So try that on your own, except you can actually make notes out of it. And if you use Pythagoras ratio, you can look up Pythagoras ratios for the distance between notes, and it's actually all fractions. So yay if you like fractions, but for some of you probably, woe is me. But anyway, you can create different ratios of notes based on just like what fraction of the water level you have left. And I don't think this is going to work on this. If I had like a wine glass or something, maybe. But if you ever take a wine glass, you can run your finger around it and make kind of like a whistling noise. And then if you lower the water level, then it'll become a deeper one. Something you could look up on YouTube maybe. There's a guy who plays one of, I think it was like Bach's Toccata and Fugue or something like that. But what he does is he lines up, it was either wine glasses or bottles, and he filled them with the right amounts of water following Pythagoras ratios. And he actually like, I think he's on rollerblades with like ski sticks, and he's got these little like spokes that come out of his rollerblades, and they run up against the bottles and play this classical piece. It's really amazing. Let's go over some of the example problems, or at least one of them. So this is the speed of sound It's a formula of 331.5 plus 0.6 times, and if you prefer, a 0.6 times the temperature in Celsius. So example 14.1. Just gonna see what 14.2. Sorry. Oh yeah. Okay. So we need to do 14.2 first, or 0.1 first. I forgot about this one. So wavelength and frequency. So I'm not gonna erase this, but we're not gonna deal with it yet. I'll just put it in the box. So frequency, we were just talking about pitch with all the instruments. Frequency equals the speed of the wave divided by its wavelength. And so we can do example 14.1 using that. 14.1 says, what is the frequency of a wave that travels at the speed of 3 meters per second? So I'll write that. 3 meters per second. And has a wavelength of 0.5 meters. Let's set this up. So the velocity is 3 meters per second. It's a big, as I call it in my algebra class, Taco Bell fraction. It's kind of like a, taco stuffed into a gordita, stuffed into a chalupa or whatever. It's like a 4-layer fraction. And then in the denominator, we have 0.5 meters, which is the wavelength. All right, so what's going to happen then, if I really wanted to, I could go ahead and do this. I could write 0.5 meters per second, make this a true Taco Bell fraction. And I'm gonna do this way, because I like this better. So how do we deal with this unruly fraction? 3 meters over seconds and 1 over 2 meters. We can go ahead and do it this way. I could rewrite this if I wanted to as 3 meters per second divided by 1 over 2 meters. And so if I do that, then, one moment please. Sorry, I needed to put the meters in the numerator. 1 meter divided by 2, because it's 0.5 meters. So now when you divide by a fraction, what are you actually doing? You are multiplying by the reciprocal. I ran out of space down here, so I'm going to move it up here. Rewrite it. So 3 meters over seconds. And instead of divided by 1 meter over 2, I'm going to say times 2 over 1 meter, because I'm multiplying by the reciprocal. Do what you do normally, cancel units. And then what do we get? We get 6 wavelengths per second, aka 6 hertz. So that's how you can calculate frequency based on knowing the wavelength and speed of a wave. Because again, frequency equals the speed of the wave divided by the wavelength. We're just going to do one example real quick, dealing with the speed of sound, calculating it. So it says if the temperature is 68 degrees Fahrenheit, aka 20 degrees Celsius, and we're going to use a Celsius measure, then what is the speed of sound in that condition? So 20 degrees Celsius. Where would we plug that in this equation? It's going to be T, which is the temperature Celsius. In order to do this, you need to have a good knowledge of the order of operations, PEMDAS, parentheses first, then exponents, then multiplication, division. You can do these as one step. Addition and subtraction, you can do these as one step. So, I've got parentheses, but everything's in parentheses, so that doesn't really affect too much. But within the parentheses, what do I do first, the addition or the multiplication? I do multiplication before addition. Therefore, step 2 of this, and I will simply erase this here. Step 2 is going to be velocity equals 331.5. I can drop my parentheses at this point. Plus, what is 0.6 times 20? That's going to be 12. I guess I'll keep my parentheses because it's all times meters per second. Yeah, I guess I need that for the unit. Then what's 331.5 plus 12? Velocity equals 343.5 meters per second. And I keep saying velocity. Sorry, I didn't mean that. The V is deceptive. You think velocity, but it means speed. Why? Because there's no directional quantity given. The speed of sound at this temperature is 343.5 meters per second. Now we're going to close off our examples by talking about something I forgot to talk about in the last lesson, which is bells and decibels. So these are for measuring the volume of sound. I wrote 2 L's, I didn't mean to. And so volume is going to translate into amplitude. So the amplitude affects the volume just like the pitch is affected by the frequency. So a bell is 10 decibels. Think deci 10 or deca 10, but deci would be like a tenth. So 10 decibels equals a bell. Why do we use both? Because a bell is actually a really large unit. So every time you go from one bell to another, you are multiplying it by 10 times the volume. So 1 bell to 2 bells is times 10. If you go from 1 bell to 3 bells, one to 3 would be times 100. And then 1 to 4 would be times 1,000. So it's not a linear scale. You're actually increasing 10 times from bell to bell, but your ear has a way of controlling the way you hear, so that like if you hear the difference between 1 bell and 2 bells, it's not going to be 10 times as loud because your ear actually has a limiting factor to reduce that in how you hear it. So 1 bell to 2 bells is by 10. 2 bells to 3 bells is by 10. So 3 bells is 10 times as powerful as 2 bells. 4 bells is 10 times as powerful as 3 bells. But if you were to jump all the way from 1 to 2 is going to be 10 times. 1 to 3 is 100 times. 1 to 4 is 1,000 times. So hopefully that makes sense. And we're going to do a quick computation using bells. For example, 14.4. All right, so in example 14.4, it says that the sound from a typical vacuum cleaner is 60 decibels, and the sound from a rifle is going to be about 140 decibels. And they ask how many times more power, or how many times louder is the rifle than the vacuum. Now, we can use that bell scale that we just did of each time you increase a bell, you're going 10 times more powerful. But to do that, we got to convert from decibels to bells. So, if 10 decibels fit into a bell, divide this by 10, and that's 6 bells. Vacuum is 6 bells. Now the rifle has 140 decibels, divide that by 10. The rifle is going to have 14 bells. So we can ask ourselves, what is the distance between 6 bells and 14? I'm going to do this by counting, not very mathematically advanced, but I just want to make this really clear. So if you can do this faster on your own, please do. I think I needed more room. I'll continue this down here. 11 bells, 12 bells, 13 bells, and 14 bells. Okay, so basically what we have is 1, 2, 3, 4, 5, 6, 7, 8. You have a difference of 8 bells. And remember, every single time you increase by 1 bell, you're going 10 times louder. Our ear doesn't hear it that way, but that's actually what you're doing. So you could do it this way very painstakingly, or you could just say, we're multiplying it by 10 to the power of 8. So from there to there is going to be 10. Just doing this to illustrate the point rather tediously. So yes, to go from 6 bells to 14, because 14 minus 6 is 8, an 8 bell difference is actually going to be a difference in volume of 10 to the power of 8. So the rifle is 10 to the power of 8 times as loud as the vacuum cleaner. 6 to 7 bells is times 10, times 10, times 10, times 10, etc. Another way to say that is the rifle is, is this in the shot? Yes, good. 10 with a total of 8 zeros times more amplitude, or louder. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So the rifle is, oh my gosh, 100 million times louder than the vacuum. Let's end off this second part of Module 14 by talking about the information that's going to be on your test. So as usual, you will fill in the blanks for certain definitions using underlined words from the module, and you don't have to do part 1 of the test. The test will be attached on ThinkWave. It's not currently, but it will be in time for you to take it. Still scrambling to get all the infrastructure up for doing these classes online, so thank you for your grace and your patience in the process. But I'll have all those tests for the rest of the year up, hopefully in the not too distant future. We also just finished buying a car, which was very time consuming, especially because the loan application had several errors in it. When I dictated it, they wrote it wrong, so we had to go back and forth a lot. But anyway, so some stuff that's going to be on the test. The definitions. You're also going to have to know about the difference between like low pitch and high pitch, and how you, you know, roughly what that is. That's a matter of wavelength affecting the frequency. They're going to give you an example where they talk about musical instruments, and you're going to have to figure out, you know, how that relates to wavelength and pitch, kind of like what I demonstrated at the beginning. Know about sound waves needing a medium to travel through, and ask yourself, like, you know, can you actually project sound into space? You can, of course, you know, an astronaut can hear sound in their spacesuit because they have an atmosphere of air around them, and then the radio signal is coming, and through a speaker, that speaker will produce sound waves that oscillate the air in the spacesuit. But if you were actually in space without a spacesuit and you had a radio just beyond your ear, you wouldn't hear it, which is kind of crazy. All right. Know about transverse waves having a oscillation and propagation that are perpendicular to each other, as compared to sorry, that was a transverse wave, as compared to a longitudinal wave, or sound wave would be an example of one, where the oscillation and propagation are parallel, going in the same direction. Now, be able to calculate the speed of sound at different temperatures, like we did in this video. Be able to calculate the frequency of sound, like we did in this video. Example 14.1 will do that. Know also about which waves have longest wavelength, whether that's like sonic, infrasonic, ultrasonic. Basically know about infrasonic, sonic, and then ultrasonic as increasing frequency or shortening wavelength. Be able to calculate the distance approximately of a lightning strike based on how long it takes the thunder to reach you. Know about which media, or mediums if you're not being very Latin, sound tends to travel fastest through, whether solid, liquid, or gas, and I think that'll probably be sufficient to know that much. But think about that chart that they have where they talk about all that. Know about again, amplitude, how that affects the volume of sound, and frequency, how that affects the pitch of sound. And know also that, basically if you have sound waves traveling at the same speed, then the difference in their frequency is going to be a matter of wavelength. All right, be able to calculate Mach speeds. So Mach 1 is the speed of sound in whatever medium it's traveling through at whatever temperature. Mach 2 would be twice that, Mach 3 would be 3 times that. And know about the Doppler effect, how that works. And also be able to calculate, just like we did in that last example, how many times louder something is depending than another thing by comparing their bells or decibels. So you might have to convert from decibels to bells, as I did, and that should do it. Thanks very much, and enjoy your homework.